before the SW1 became a household name in railroad circles, before the NW2 proved diesel could dominate yard service, before EMD became synonymous with American diesel power. There were a handful of boxy, unpretentious locomotives that quietly validated an entire concept: the NC Series switchers, built between 1935 and 1939, underpowered by later standards, mechanically temperamental. But they worked, and more importantly, they taught the Electromotive Corporation lessons that would shape the next 40 years of American railroading. These were the machines that proved diesel-electric locomotives could replace steam in the most demanding environment railroads faced: the classification yard. Without them, America's diesel transition might have stalled in the early 1940s, delayed by skepticism and unproven technology. This is the story of the switchers that changed everything, then disappeared. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. To understand why the NC series mattered, you need to understand what railroad yards were like in 1935. Steam switchers dominated every classification yard, every industrial spur, every port facility in North America. Typically 0-6 narrow or 0-8 narrow wheel arrangements. Heavy, powerful when moving, but operationally inefficient in ways that cost railroads enormous sums. A steam switcher consumed fuel even while standing still. The fire had to be maintained constantly. Water levels required monitoring. Boiler pressure couldn't drop below operational minimums. This meant a switcher burning coal or oil for 16 to 20 hours daily, even if it only moved cars for 8 of those hours. The crew requirements were substantial: engineer, fireman, sometimes a hostler to manage the locomotive between shifts. Each shift change required time for the incoming crew to assess boiler condition, water levels, fire intensity. Maintenance intervals were frequent: ash removal, boiler washouts every 30 days, running gear inspection, valve timing adjustments. The steam switcher was a machine in constant need of attention. But the real operational problem was thermal lag. A cold steam locomotive required 45 minutes to an hour to build working steam pressure. This meant switchers stayed in service continuously, burning fuel around the clock, because the alternative was unacceptable delays when switching work needed to begin. The Great Depression forced railroads to examine every operational cost. Track maintenance could be deferred, capital improvements could wait, but yard operations continued regardless of economic conditions. Freight still needed sorting, local deliveries still required switching, and steam power was bleeding money in ways that were becoming impossible to ignore. The railroads needed something fundamentally different, not a better steam switcher, something that didn't burn fuel while idle, something that started instantly, something that required fewer men and less maintenance. Diesel-electric technology existed. The concept was proven in marine applications, mining equipment, and stationary power generation. General Electric had experimented with diesel-electric locomotives. So had Ingersoll Rand, Alco, and Baldwin. But no manufacturer had yet produced a diesel switcher reliable enough, economical enough, and available enough to replace steam wholesale. The Electromotive Corporation believed it could solve this problem, but it needed to prove it, not with promises, not with projections, with actual locomotives operating in actual service. The NC series was that proof. In 1935, Electromotive Corporation was not yet the General Motors subsidiary that would dominate post-war diesel production. EMC was an independent company founded in 1922, primarily focused on building self-propelled rail cars and small locomotives using engines purchased from other manufacturers. The Winton Engine Corporation supplied EMC's diesel power plants. General Electric and Westinghouse provided generators, traction motors, and control equipment. EMC's contribution was integration, taking components from multiple suppliers and creating a functional locomotive. The NC designation followed EMC's emerging naming convention. N indicated a switcher locomotive, distinguishing it from the E passenger units and later F freight units. C stood for cast underframe, a critical engineering choice that separated these locomotives from earlier fabricated frame designs. The cast steel underframe was expensive to produce, but offered significant advantages. It provided a rigid, integral structure that reduced flexing under load. The fuel tank was cast as part of the frame, eliminating potential leak points. Traction motor mounting points could be machined to precise tolerances, improving gear alignment and reducing wear. Most importantly, the cast frame allowed EMC to create a standardized platform. Once the casting patterns were made, each frame would be functionally identical. This meant predictable performance, simplified maintenance, and easier parts inventory management. The NC series used the Winton 201A engine, an 8-cylinder, 2-stroke diesel rated at 900 horsepower. This engine was adapted for marine applications. It featured uniflow scavenging, where intake air entered through ports in the cylinder liner, and exhaust gases exited through poppet valves in the cylinder head. The 201A was not a refined power plant. Bearing failures were common. Piston rings wore rapidly. Oil consumption was high by later standards. But it had one critical advantage: excellent low-speed torque characteristics. The 2-stroke design produced a power pulse every revolution, not every 2 revolutions like a 4-stroke engine. This meant smoother power delivery at the low speeds typical of switching service. The electrical system used a main generator driven directly by the diesel engine. This generator produced direct current that fed 4 traction motors, 1 per axle in a BB truck arrangement. The engineer controlled power output by adjusting engine speed, which changed generator output, which altered current to the traction motors. Early NC units used General Electric GT551 generators, though specifications varied depending on individual railroad requirements. Control stands were simple by later standards: throttle, reverser, brake handles, and basic gauges. No dynamic braking, no wheel slip protection beyond manual sanding. The engineer relied on experience and feel to avoid burning out traction motors or spinning wheels. Variations emerged quickly. The NC1 and NC2 designations indicated electrical system upgrades as EMC refined control circuits and improved generator efficiency. The NW designation appeared when EMC switched from cast frames to welded frames, reducing manufacturing cost while maintaining structural integrity. The NE models were lighter, lower-powered variants rated at 600 to 800 horsepower. These were intended for industrial customers with lighter switching requirements: paper mills, cement plants, small ports. The NE units used 6-cylinder Winton engines but retained the same basic electrical architecture. Production numbers were modest. Fewer than 50 NC series units were built between 1935 and 1939, but they went to railroads that mattered. Santa Fe purchased several for evaluation in California yards. Illinois Central tested them in Chicago. Southern Railway used them in Atlanta Terminal Service. Missouri Pacific, Milwaukee Road, and New York, New Haven, and Hartford all operated NC series switchers. These railroads weren't buying production locomotives. They were buying proof-of-concept machines. Every operational hour generated data. Every maintenance issue revealed design flaws. Every successful shift proved that diesel could work. The Winton 201A engine sat longitudinally in the locomotive frame, directly coupled to the main generator. 8 cylinders arranged in a V configuration, 4 per bank. Bore and stroke dimensions of 8 inches by 10 inches. Compression ratio around 17:1, typical for compression ignition engines of the period. The 2-stroke cycle required forced air induction. A Roots-type blower, gear-driven from the crankshaft, supplied pressurized air to scavenge ports in the cylinder liners. As the piston descended, it uncovered intake ports, allowing fresh air to sweep exhaust gases through the open exhaust valves. This uniflow pattern prevented exhaust gas contamination of intake air, improving efficiency. Fuel injection used mechanical unit injectors, 1 per cylinder. Injector timing and fuel quantity were controlled by a camshaft-driven mechanism. Fuel pressure reached approximately 1,500 pounds per square inch at the injector nozzle. The system was relatively crude compared to later designs, but functionally adequate for switching service. The crankshaft drove the main generator through a flexible coupling that absorbed torsional vibration. Generator output varied with engine speed. Higher RPM meant higher voltage and greater current capacity. The engineer controlled this relationship through the throttle, which adjusted engine governor settings. Electrical control was entirely electromechanical. Relays, contactors, and manual switches routed power from the generator to the traction motors. The reverser handle determined motor polarity, controlling direction. Transition relays could reconfigure motor connections from series to parallel operation. Though this feature was often omitted or simplified on early NC units, the 4 traction motors were mounted in the trucks, 1 per axle. These were nose-suspended designs. One end of the motor mounted to the truck frame, the other end carried a pinion gear that meshed with a bull gear on the axle. As the axle moved over track irregularities, the motor pivoted slightly, maintaining gear mesh. This arrangement transmitted all traction forces through the motor housing, subjecting the motors to severe mechanical stress. Bearing failures and gear wear were persistent problems. But the design was simple, compact, and allowed motors to be removed for service without disturbing the truck frame. Cooling presented significant challenges. The Winton 201A generated substantial waste heat. The electrical equipment added more. The locomotive needed cooling capacity equivalent to a small industrial plant, packaged into a 20-ton machine. EMC used horizontal radiator sections mounted in the hood. Multiple belt-driven fans forced air through the radiator cores. Thermostatically controlled shutters modulated airflow, maintaining optimal coolant temperature regardless of ambient conditions. The cooling system was entirely mechanical. No electric fans, no complex controls. This simplified maintenance but made the system sensitive to belt tension, shutter adjustment, and radiator core condition. Overheating was a common complaint, particularly in hot weather, or when locomotives were worked hard in continuous service. The cast underframe integrated the fuel tank, typically holding 500 to 600 gallons. This provided 8 to 10 hours of operation at normal throttle settings. The frame also incorporated mounting points for brake equipment, air reservoirs, and battery boxes. The cab was centered on the locomotive, providing good visibility in both directions. The engineer sat in the center, with controls arranged in a semicircular pattern. Early units had minimal amenities: steel seat, basic gauges, minimal weather protection. Comfort was not a design priority. Limitations were numerous. The Winton 201A was prone to bearing failures, particularly at the generator end where loads were highest. Piston ring wear was excessive, leading to high oil consumption. Exhaust valve guides wore rapidly, causing blow-by and power loss. The electrical system lacked sophistication. Wheel slip could damage traction motors before the engineer could react. Transition between series and parallel operation, when available, was abrupt and required skill to execute smoothly. Sand capacity was limited. The sandboxes held perhaps 50 pounds per box, enough for a few hours of switching in wet conditions, but inadequate for sustained operations in rain or snow. The braking system was straight air, not the automatic air brakes used on road locomotives. This simplified the design, but meant the NC series was restricted to yard service and short industrial spurs. Despite these limitations, the NC series worked. They moved cars, they performed switching. They demonstrated that diesel-electric power was viable. The operational impact of NC series switchers became evident within months of entering service. Startup time dropped from 45 minutes to 45 seconds. An engineer arriving for a shift simply climbed aboard, started the diesel, confirmed oil pressure and generator function, and began switching. No fire to build, no steam pressure to wait for, no boiler to inspect. Fuel consumption changed dramatically. A steam switcher might burn 3 to 4 tons of coal per day, regardless of how much actual switching occurred. An NC series unit consumed fuel only when the engine ran, and fuel consumption tracked power output directly. Operating at idle required minimal fuel. Full power demanded more, but the relationship was linear and predictable. This fundamentally altered yard economics. Railroads could now calculate switching costs per car, handled, not per day of operation. The NC series demonstrated that diesel power was measurable, predictable, and manageable in ways steam never was. Maintenance intervals extended. Weekly inspections replaced daily boiler washouts. Oil changes occurred every few hundred hours instead of constant water and coal handling. Repairs happened on schedule rather than in response to failures. Crew requirements decreased. Most NC series switchers operated with a single engineer. No fireman was needed. Some railroads assigned a second person for safety or union contract reasons, but the locomotive itself required only one qualified operator. Yard efficiency improved measurably. The NC series could cycle cars continuously without thermal brakes. Classification work proceeded without interruption. Switching moves that required careful coordination with steam locomotive availability could now occur on demand. Industrial customers became early adopters. Steel mills used NC series switchers to move ladle cars, scrap gondolas, and finished product loads through plants that generated enough heat without adding steam locomotive exhaust. Cement plants valued the consistent power output and reduced fire risk. Port facilities appreciated the quick response and minimal warm-up time. Paper mills and chemical plants found that diesel switchers reduced contamination concerns. Steam locomotives scattered ash and cinders. Diesel exhaust was cleaner, more predictable, and less likely to damage finished products or sensitive processes. These industrial installations provided crucial operational data. They worked NC series switchers hard, often 24 hours daily. Maintenance records from these operations revealed failure modes, identified weak components, and demonstrated which design features worked reliably under sustained use. The standardization inherent in diesel-electric design proved transformative. Steam switchers varied by builder, by railroad, by era of construction. A Chicago and Northwestern 0 to 6 Nero might share no parts with a Southern Pacific 0 and a 6-0. Maintenance crews needed different tools, different knowledge, different parts inventory for each steam locomotive class. NC series units were functionally identical, regardless of operator. Traction motors were interchangeable. Electrical components followed standard specifications. Even the Winton 201A engines used common parts across all installations. This meant a railroad could stock one set of spare parts for an entire fleet of NC series switchers. Maintenance personnel trained on one unit could work on any unit. Repairs became routine rather than custom fabrication exercises. Railroads began to understand that diesel power offered more than operational advantages. It offered predictability, budgetable costs, quantifiable performance. These were qualities steam locomotives simply couldn't match. The NC series units themselves were far from perfect. Winton 201A reliability remained problematic. Overheating occurred frequently in summer operations. Traction motor failures were common enough to require strategic spare inventory, but the concept was proven. Diesel-electric switchers could replace steam. They could do so economically. They could do so reliably enough for daily railroad operations. By 1939, every major railroad understood that diesel switching power was not experimental. It was practical, proven, and soon to be essential. The Winton 201A engine was the NC series' fundamental limitation. Bearing design was inadequate for continuous heavy load operation. The crankshaft itself was marginally sized for 900 horsepower output. Piston ring wear led to excessive oil consumption and blow-by. Most critically, the 2C1A suffered from a design flaw in its lubrication system. Oil pressure fluctuations under varying load conditions led to bearing damage. Once a bearing began to fail, the engine could self-destruct rapidly. Rebuilding a 201A required specialized knowledge and often revealed additional damage that made the repair uneconomical. EMC recognized these problems. By 1938, the company was developing a replacement, the 567 engine. This designation referred to the displacement of each cylinder in cubic inches. 12 cylinders times 567 cubic inches equaled nearly 7,000 cubic inches total displacement. The 567 was a clean sheet design. It retained the two-stroke cycle and general architecture of the 201A, but corrected virtually every reliability problem. Bearing sizes increased. Lubrication passages were redesigned. Piston ring design improved. Crankshaft strength margins expanded. In 1939, EMC introduced the SW1 switcher, same basic concept as the NC series. Diesel engine, main generator, 4 traction motors, B trucks. But powered by the 5N67 engine, rated at 600 horsepower in 6-cylinder configuration. The SW1 was less powerful than the NC series on paper, but it was vastly more reliable. Maintenance intervals extended, overhaul life increased, operating costs decreased. The SW1 could work continuously in ways the NC series never could. Railroads responded immediately. SW1 orders began arriving by the dozens, then by the hundreds. The NW2, a 900 horsepower version using an 8-cylinder 567, followed in 1939. The NW designation was retained, acknowledging the NC series lineage. but the locomotives were entirely new machines. The NC series became obsolete almost overnight. Railroads with NC units continued operating them, but no one ordered more. No one rebuilt them with upgraded components. The tooling and patterns for NC production were retired. EMC's focus shifted entirely to 567-powered locomotives. By the mid-1940s, most NC series switchers were relegated to secondary service, light industrial switching, standby duty, any work that didn't require high reliability or continuous operation. By the 1950s, retirement began. The Winton 201A parts supply dwindled. Traction motor failures became expensive to repair. Railroads that had purchased SWA1 or NW2 switchers found maintaining the older NC units increasingly difficult. Scrappers claimed most NC series locomotives by the early 1960s. A few survived in industrial service into the 1970s, but only because they saw minimal use. The mechanical complexity and parts scarcity made them uneconomical compared to newer diesels. Preservation was almost non-existent. The NC series had no nostalgic appeal. They weren't streamlined passenger locomotives. They weren't powerful freight haulers. They were boxy industrial machines that few people outside railroad operations even noticed. Today, virtually no complete NC series switchers survive. A few components exist in museums. Some technical documentation remains in railroad archives, but the physical machines are gone. Yet their legacy is everywhere. The cast underframe concept influenced every subsequent EMD switcher design. The standardized cab layout became the template for SW and NW production. The electrical system architecture, refined and improved, powered EMD locomotives for decades. The operational data generated by NC series switchers demonstrated diesel's advantages conclusively. When EMD launched full-scale production in the 1940s, skepticism had evaporated. Railroads knew diesel worked because the NC series proved it. The SW1, NW2, and later SW7, SW9, and SW1-1200 switchers became America's standard yard power. Tens of thousands were built. They dominated railroad yards until road switchers and larger units made dedicated yard locomotives less necessary. Every one of those switchers descended directly from the NC series experiments. Every design decision, every engineering refinement, every operational improvement built on lessons learned between 1935 and 1939. The NC series taught EMC how to build diesel locomotives that railroads would buy. They revealed which features mattered and which were unnecessary. They exposed weak components that needed strengthening. They demonstrated which suppliers produced reliable equipment and which didn't. Without the NC series, EMD might have spent years learning these lessons on production locomotives, damaging the company's reputation and slowing diesel adoption. Instead, EMC absorbed the pain of experimentation with a few dozen prototype units, then launched production models that worked reliably from day one. The NC series switchers were never meant to be famous. They were development platforms, test beds, proof-of-concept machines that allowed EMC to learn the diesel locomotive business before committing to mass production. They succeeded in that mission completely. By 1939, when the last NC units were delivered, EMC had become confident enough in diesel technology to design and produce the FT freight locomotive, the machine that would ultimately displace steam from mainline service across North America. The FT program succeeded because EMC had already solved switching service with the NC series and refined that knowledge with the SWA1. The engineering team understood diesel reliability. They knew how to specify electrical components. They had relationships with suppliers. They had trained maintenance personnel and established parts distribution networks. All of this came from building fewer than 50 NC series switchers. The diesel transition transformed American railroading. By 1960, steam locomotives had virtually disappeared from Class I railroad service. By 1970, even the smallest short lines had dieselized. The economic advantages were too substantial to ignore. This transformation began in classification yards with boxy, unremarkable switchers that proved diesel could work. The NC series was the first step. Not the only step, but the necessary first step that made everything else possible. They were the forgotten pioneers, the experimental machines that validated an idea, the prototypes that taught a company how to build locomotives that would power America's railroads for the next 50 years. Every modern locomotive, whether EMD or GE or any other manufacturer, owes something to those early NC series switchers. They proved the concept. They revealed the problems. They demonstrated the path forward, and then they disappeared, their purpose fulfilled, their legacy embedded in everything that followed.